Well, hey there, HVAC pros and enthusiasts. Are you ready to take your skills to the next level? The HVACR Learning Network has just launched an exciting new e-learning course, High Performance Heat Pumps. And guess what? We're giving you free access to the first 2 chapters. Whether you're in the field, training for that next step, or simply want to sharpen your expertise, this course is packed with everything you need to understand and master high-performance heat pump systems, especially inverter-driven cold climate heat pumps. And the best part? You can access it anytime, anywhere, right from your favorite mobile device. It's HVACR learning made flexible and convenient for you. So what are you waiting for? Click the link. Dive into the HVACR Learning Network and start your free trial today. Your journey to HVACR mastery begins here. Well, hello everyone. Thank you so much for joining us once again on Did You Know, the ESCO HVAC show. I'm so grateful that you're taking time out of your day to be here with us. Jason Johnson, that's right. Glad to see you here. If you have any questions along the way, just let us know in the chat. We'll be happy to dive a little bit deeper into things. You're right. That's what we're here for, is to learn something hopefully new, or at least give us a refresh on things that we've had some experience with before. Let us know in the chat where you're joining from. I have the most amazingly blessed opportunity to be here at the 2025 National Skills USA Conference and Competition. Froggy Beluga, hey, glad to have you here. And so this is actually the competition floor behind me. And I apologize for last week. I was on vacation. We had a newly released video from Johnson Controls that we were going to play, and we had some hiccups in the background. So I know y'all didn't get to see that. We're going to do that. I think we're going to do that one next week. And for this week, we're going to be able to have this in the background, show you a little bit about what's happening here, but then we're going to dive deeper into thermostatic expansion valves and electronic expansion valves with, oh, hey, what's going on there? With Brian Dail from Danfoss. How you doing, sir?
I'm doing great. Yeah, happy to be here. Yeah.
So Brian, where are you joining us from today?
So I'm working out of my home office in my basement in Ann Arbor, Michigan.
Very, very cool. So I'm here in Atlanta. And for those of you that don't know about Skills USA, it's about 6,500 competitors from high school into college vocational style competitions, and anything from culinary all the way to HVAC. So we've actually got 60 competitors here, and we're doing a whole lot back in there somewhere. And actually, while we're here, I'll go ahead and move things around so everybody can see what we're talking about. So I'm in just one of the facilities here at the Atlanta Convention Center, and we are just talking tons and tons and tons of competitions. I'll have some other videos about this, kind of showing you what they do here at Skills USA. And for those of you instructors that have students that are in the competition, we're grateful that you send them here. And for those that don't, we encourage you to learn more a little bit about Skills USA and ways that you can introduce your students into things like this, which you have opportunities for scholarships and opportunities to talk to some of the potential employers when you get out of there. So Brian, tell us a little bit about your history, your experience in the industry.
Yeah, so I've been in the industry about 15 years now. I started working for a Sportland Valve Company, Parker, when I first got out of college in 2010. I've been with Danfoss now about 8 years, been in application engineering, spent a little bit of time in our marketing group, and I'm back now as application engineering manager. And a lot of experience with valves, compressors, heat exchangers, troubleshooting out in the field. Not a lot of holding tools in my hands. A lot of troubleshooting though, and a lot of job site experience. So
No, absolutely. And we encourage having that here on the show. So we have different aspects of our industry. We have engineering, we have manufacturing, production, we have technicians that are doing technical support, seeing the whole different aspect of what our industry is. And so we're glad to have you here. And if you ever want to get out in the field and see some of these little things in action, we can make that an arrangement sometime. Jason, you bring up such a good point. This is why we want to have this conversation. We've seen that transition, especially in the residential and light commercial, from fixed orifice like piston style metering devices, and then we moved into thermostatic expansion valves. And a lot of the industry sees electronic expansion valves as a small piece of the industry, but that is not so. We're moving into electronic expansion devices in a very fast way. And so we want everyone to have a better understanding of how they operate, how they're different, and how we can do diagnostics on each of those. So, Brian, I'm going to go ahead and pop on over, and I'll let you run with the show, and I'll keep an eye on things over here on the side and help answer any questions, and then probably have some questions of my own throughout the show.
Great. Well, feel free to ask questions. Put them in the chat, and they'll be brought into me. I like answering questions. Helps let me know I'm saying something that people are interested in.
Absolutely.
So, the goal today is talk about TXVs versus EXVs, get a little bit into the operating differences, myth busting, and close out with some troubleshooting. So just got up here some pictures of different TXVs and EXVs made by Danfoss, but TXVs and EXVs work in pretty similar ways between different manufacturers. So everything I say here should be, for the most part, pretty interchangeable with different manufacturers of TXVs and EXVs. So the main thing I want to start off with is, well, why do manufacturers choose a TXV versus an EXV, and when are there advantages versus disadvantages of either product? And the first one's just kind of getting down to brass tacks. A TXV is going to be a lower cost than a EXV. And the reason for that isn't because of the valve itself. A TXV versus an EXV, oftentimes they're very similar in price. What makes an EXV more expensive is, well, you need a controller, and that controller has to have a power supply. And then you have to have sensors, and then the sensors are there to measure pressure, and sensors that are there to measure temperature. And when you add all that stuff up, all those extra items, it makes an EXV overall more expensive than a TXV. So all things being equal, a manufacturer is going to prefer to use a TXV, and you're going to prefer to have that because it makes for a lower first cost. So if you're going to use a EXV, it needs to be in a situation where you're able to take advantage of the advantages that it can bring you. And as time goes on, you might just see more EXVs because there's already going to be more electronics in the system. If there's more electronics, it makes some of these other costs kind of go away. If there's already a pressure transducer to give a low suction pressure alarm, well, now you don't have to add that to the cost. And if all these electronics are already in there, it makes the cost of that EXV not so expensive, and it makes it an easier switch to make.
Yeah, when we start looking at that progression of equipment, we have many manufacturers of equipment that are here represented at the conference, and they all say the same thing, that the days of single stage and two stage equipment, especially in the residential light commercial split system era, are just about ending, and that the only single stage equipment that they're going to be using is going to be their builder grade, and that a majority of their products are starting to move from TXV into EXV components. So it's critical that we understand how they operate as they start moving into the market even further.
Definitely, I agree. So one of the things to start with is oversized TXVs tend to hunt. And for a balance ported TXV, they can still operate pretty effectively down to 25% of their rated capacity. But once you get them down near that point, they get pretty jumpy. EXVs typically have a pretty linear flow characteristic. They can control stably down to at least 10%, if not lower than that, of their rated capacities. And there tends to be very little hysteresis with them. So they can be very precise. assuming the algorithm that's set up to control them is well designed, well established, well tested. And this makes it so that EXVs work really well in a variable capacity system, whether it's a set of tandem compressors or a compressor with a VFD on it. If you've got a system that's got a 4-to-1 turn down ratio, so a compressor that can run up at 6,000 RPMs versus 1,500 RPMs, your TXV is going to be hunting by the time you get down to 1,500 RPMs. Even sometimes if you just have a 2-to-1 turn down ratio, you go from 3,600 RPMs to 1,800 RPMs, even there, sometimes the TXVs can start to be hunting as it starts to get to the low end. So that's one thing where if you use an EXV, you don't have to deal with that hunting problem. Sometimes still, a TXV can be used in those situations, because if you're getting some hunting at your low speeds, if you've got an accumulator, the coil is well designed, maybe the superheat settings set a little bit higher so that it's hunting from, in a range that's, you're not floating back to the compressor, you can still get away with using a TXV, but that's where EXVs can really provide an advantage. EXVs can safely provide lower superheats in variable capacity systems and improve efficiency. And that's true whether you're working on a gigantic chiller. Someone in the chat mentioned working on some ETS 400s. Those are going to be used on 400-ton R134A circuits, maybe a different refrigerant, but one of those low pressure refrigerants. But that also applies to when you're using a EXV or a TXV in a residential system. That you can get away sometimes with an oversized TXV, but the EXV is going to provide more efficiency if it's set up properly.
I seen that transition myself when I was in the refrigeration. So I spent most of my career as a mobile engineer in commercial refrigeration. And so in the grocery stores, I had 2 generations that I worked on. The older stores that were made pre-2000 that were all, semi-hermetic up through, 60 rack systems, a lot of Tyler rack systems. And those, even then, we still use thermostatic expansion valves in the cases until we started doing unloaders and started having some modular capacity on our racks. And then we would start converting some of the major loads, our walk-in coolers, walk-in freezers with electronic expansion valves. But by the time we got into no later than 2010, all of the new stores were being manufactured with variable capacity systems. They were using like Hussmann protocols that were completely variable, that were using scrolls that were digitized, and everything went to electronic expansion valves. So we're talking 15 years or more ago, we started making that conversion. And a lot of people don't realize how many electronic expansion valves are in the industry just waiting to be found.
Yeah, they're everywhere. In this presentation, most of my examples are kind of aimed at air conditioning type stuff, but all this advice is going to apply in refrigeration applications too. I don't have a picture of a supermarket case in here, but it'll work just the same in a supermarket case. So yeah, and it's a lot of the same calculus. A TXV by itself in a supermarket case is going to be cheaper than having to get a case controller and the driver and the EXV and the sensors. But more and more in these cases, they want to make them dual temperature and things like that. So there's already a lot more electronics in there anyway. So if you already got a lot of electronics in there, it doesn't make it quite as expensive to add in that EXV compared to a TXV. And then you can take advantage of some of those control advantages. So yeah, great. TXVs have one setting. Most of you out there that have some experience, you've seen the adjustable TXVs where you turn it in and dial in. In a lot of residential air conditioning, they've already tested it and in their labs, and they give a fixed valve. In fact, I can go back to my first slide here.
Yeah, there we go. Just so people know what we're talking about.
Yeah, there's adjustable TXVs and there's fixed setting TXVs. The fixed setting ones, those are going to be used in the builder grade residential equipment, and that's because if we don't have that adjustment stem in there, it gets to be a little bit lower priced valve, and also the manufacturer knows no one can ever go through and mess with it. So a residential air conditioning manufacturer can figure out a setting in their lab that works good for their system, and they ship out a valve that's got no adjustment stem on it. But so whether it's a non-adjustable valve that is coming from the factory with its own setting, or it's a adjustable valve that you're able to dial in yourself on a piece of equipment. Once you've set it, it's set. Now it's got its superheat setting. It can't do anything else. I guess in theory, someone could have you come back each season and adjust it, but yeah, that just doesn't happen. So
Right.
that's the difference between the two. And a TXV is going to have one setting, and it's going to and that valve on its own will then measure and control to superheat based on that one setting. If you have an EXV, you're directly measuring superheat, and you've got a controller on there that's got an algorithm and a program in it. And whatever superheat it's controlling to, that can adjust in different seasons. It can adjust based on different loads. It could know, hey, when the compressor slows down, maybe I should let the superheat setting drift up a little bit higher. It gives the system manufacturer more options inside their controller for how that EXV should control based on other factors other than just what superheat's being measured at the evaporator. And what you might find a lot of times is on residential systems, the indoor coil might still have a TXV, but that outdoor coil on the variable speed condensing unit, that'll almost definitely have an EXV on there, because in a residential system, the indoor evaporator temperature coil tends to be pretty steady in its temperature. Yeah, as the seasons change, if you had your gauges on there, you'd see the evaporator temperature drift around a little bit. It might go from 50 down to 45, back up, but it's a pretty narrow range. If you look at that condensing unit, that temperature moves all over the place. And then if it's a heat pump, it's really moving all over the place. You're heating. You might be heating when it's 50 degrees outside. You're also going to be heating when it's 0 degrees outside. So look at that wide range in evaporator temperatures you might see on that outdoor coil. And that really gives a big advantage to a EXV, because you're directly measuring with a pressure transducer and a temperature sensor what that superheat is on that outdoor coil. And when you've got the TXV, you've got the bulb and the external equalizer, and it's measuring superheat, but it's not as precise as a digital computer can be. And you can now dial in what you want that superheat to be based on different outdoor temperatures. And it can make for a much more efficient system, instead of having a TXV that just has one setting and now has to try and manage over this wide range of evaporator temperatures and a wide range of compressor speeds too. So it gives an opportunity for an EXV to be a big advantage in those types of applications. However, they are only as good as their algorithm. It takes a lot of effort on the manufacturer's part to write a good program and to test it and make sure it works as intended. So there are some trade-offs there, but they do have the ability to be a lot better given the resources.
I've seen a big change over the last decade in that residential, like commercial split system, even package unit, RTUs. We've really seen a lot of those adjustable thermostatic expansion valves up until a decade or so. And then I've noticed a lot of our equipment have been using, fixed thermostatic expansion valves. And so with those fixed thermostatic expansion valves, we're also assuming, that system is tuned properly for the system that we're working on. And unfortunately, there is no control of those. Where they come is where they run. And many a times they have a much wider, float bandwidth than what we see in some of our adjustables. So when we look at the accuracy, typically people would think, okay, we go from piston, we're going to a thermostatic expansion valve. There's a huge difference. Why would we need to go to electronic expansion valve? Well, there's times when we go into the fixed thermostatic expansion valves that we have a really wide window of operation, a lot of float, which we wouldn't see in those electronic expansion valves like you're talking about when they're really finely tuned.
Mm-hmm. Yeah, there definitely can be, because as the conditions change, the superheat that TXV controls to shifts around. So this is a simple slide. If you've gone through any sort of refrigeration or air conditioning training course, you've seen a slide like this where it's just talking about measuring superheat. And it's very important to remember TXVs and EXVs, they're both superheat control devices. So if someone's telling you, oh, hey, I'm having a problem with the TXV or an EXV, first question I always ask them is, what's your superheat? And if someone can't give me an answer to that question, I always know, okay, let's go back to the draw. Let's take a few steps back.
Brian, it's good. I know. I'm telling you, it's good.
Yeah, and that always leads to the question. Okay, and what value is good? So Here it's a example, 8 degrees superheat leaving an evaporator, and you calculate that the same way whether it's a TXV or EXV. Ideally, when you're measuring superheat, you want to get as close to the evaporator as possible. And I think a good thing to also consider too is if you have an EXV, where's the pressure transducer at? And when you've got a TXV, where's the external equalizer at? Because generally it's supposed to go right at the outlet of an evaporator, but you might sometimes see manufacturers do things where they put it after the 4-way valve before the compressor. And that's also a fair way to do things, because you're now trying to protect the compressor by controlling superheat coming back to it. It just kind of depends. So if you're looking to troubleshoot, a good thing to consider is, well, where do they have the bulb? Where do they have the external equalizer? Where is my temperature sensor? Where is my pressure transducer? And that might help give you at least an idea. If you're measuring superheat entering the compressor, you expect it to be higher than what it is at the evaporator coil itself. And then depending on how long your runs are, is there a 4-way valve there? Those things might give you clues as far as, well, yeah, it should be much higher at the compressor than it is at the evaporator, and vice versa. So.
There's a general procedure within the industry for that placement of that sensing bulb. And we typically say, between 10 and 2 on the top side of the tubing, but that's not always the case. It depends on exactly where the manufacturer wants that to be, especially when we're talking about blended refrigerants. So this is a very timely conversation when we start thinking about our transition into A2L refrigerants. We're going to be working with, you're going to be working with a blended refrigerant that has a little bit more glide than we have seen in the past. Every 400 series refrigerant is a blended refrigerant, potentially has some glide, like R410A, there was a little bit, right? So we had a very little bit of glide. As we move into 454B and a variety of other 400 series refrigerants, whether you're working in air conditioning or refrigeration, we have to be aware of those variations of that glide between those boiling points. It can be critical for the placement of that bulb. And then in many times it widens that window of operation for controlling superheat. And that's the reason we're going to start seeing a lot more electronic expansion valves, so we can start fine tuning and programming these things for optimal operation.
Yeah. So with TXVs, the bulb, it can be, there's the picture that I've got in the instruction manual when we sell a TXV, but we understand the real world's different. And also manufacturers, especially residential ones where they do a lot of testing and they do a lot of high volume, they can't fit it in a certain spot. They find they get better performance, so they put somewhere else. Trust the manufacturer's recommendations for where they put it. But yeah, it's something to take a look at as always. Superheat's important. So is subcooling. And I'm sure everyone's seen charts like this before where you go through and calculate subcooling, but an EXV needs subcooling to feed. The same way that a TXV does. It's a very small opening in any TXV or EXV, and it's meant to have 100% liquid on it so that it can feed. If vapor starts getting in the way, because it's such a small opening, it won't be able to get enough through, and you'll underfeed as a result. If you have little to no subcooling, you should also have high superheat, and there's nothing that TXV or EXV could do to fix that. You have to whether it's clean your condenser, add more charge, find the kink in the liquid line, whatever it may be, replace your filter dryer. I probably could go on and say more things that it could be, but superheat and subcooling, they're basics, but they're important for a reason, because they can tell you a lot about what's going on in a system, and they can also give you a lot of good ideas on how to go search for what the problem might be. And a lot of what I go through here is going to be giving you advice on how to better go through troubleshooting. There's never going to be like one magic bullet that's going to work every time, but you just got to keep taking in more information and then making the next choice of what to go check until you've got a full picture and you can fix the issue. Another thing that EXVs can't do is fix pour distribution in an evaporator. So in a evaporator, if you have poor distribution that can create big problems and lead to hunting. And when I say unequal distribution, I mean this in two different ways, and both have the same basic effects, which is if you have a distributor that doesn't equally distribute refrigerant to each one of the circuits in your evaporator, or your ductwork is set up in a way so that you're not getting even airflow across all the circuits in your coil, you're going to have refrigerant evaporating off at different rates. And then you'll have certain circuits that can flood back while other circuits are starving. This example of what I'm showing here, it's showing two circuits at a pretty good level. This refrigerant's boiling off just before you get to the exit, but two other circuits where you've got liquid coming into your suction header. And so when that happens, that generally leads to a hunt. And this is going to be a problem whether you've got a TXV or EXV. And generally, the way that, with the distributor, if you can't get that design perfect, you can't get that airflow perfect, it's because of the way the shape of the coil, the way the fans brings in air, it makes it so that it's, you're not always able to get perfect distribution. And then when you're setting the superheat, whether it's with a TXV or an EXV, you set it so that you get it as low as you can, but have none of those circuits flooding back. So if you were to measure superheat in each one of these circuits, you might see, well, some of them are at 3 degrees and others are at 10, and then it all averages out. And what you need to make sure, and comes from manufacturers that are testing systems, they have to make sure that they never get to zero in any of those circuits. And that's generally is how a TXV or EXV's superheat set point gets determined, to make sure you don't have flood back through any one of these individual circuits.
I'll get questions on this every once in a while of, what kind of scenarios could we see something like this? Well, an example I use all the time here in the Midwest. So in the Midwest, Indiana, where I'm from, a lot of our installations are counterflow. They're downflow furnaces with a coil underneath of the furnace. And because in the wintertime, it gets very dry here, we add a bypass humidifier. And now, since we don't have a ductwork to tie on our bypass, we'll cut a 6-inch hole in the side of the evaporator case. And that is where our bypass line connects from the humidifier. And when we do that, now we're completely redistributing air. And if, I shouldn't even say if, I say when the homeowner doesn't redistribute our airflow, we're actually changing the way air is flowing across our coil because we're sending some of that through that bypass line. Mm-hmm. And will absolutely cause a poor distribution through our separate metering flows.
Absolutely. Yeah, I hadn't thought of that example, but that's an excellent one. I've got one on my house myself. It doesn't come back in directly to where the evaporator coil is, so I hope it's not causing an issue. But I should probably think about that myself. So.
Yeah, it's very common when in the industry that's overlooked in residential applications, at least here in the Midwest. And because during that cooling, we lose a portion of our airflow, and now all of a sudden we have unequal airflow, through the evaporator, especially when we start looking at multiple slab coils like N and M coils. It really can have an effect on that. And so that understanding how, like you said, how the superheat is flowing through the coil is critical, because it's looking at more of an average, really.
Yeah, and this is one of the examples where an EXV could actually perform worse. If you have poor airflow, if you have a air filter that starts to get blocked up and you start to really restrict that airflow, an EXV could perform worse because it's digital, it's getting an exact measurement. Whereas the TXV, it kind of takes time for it to heat up and cool down. It's kind of doing its own thing, and then it eventually starts reacting. So I've seen situations where installation of EXVs has led to worse performance because it is precise, and TXVs kind of slough along through some hunting, and the EXV reacts quickly, and it restricts too much as a result. So, yeah.
Not saying that there are improperly commissioned systems in our industry without saying that we have a lot of improperly commissioned systems in our industry. One of the things that we used to think of a lot of times when we're looking at adjusting our airflow on an air conditioning system, many times if we're wanting to readjust our sensible heat ratio, we would reduce airflow a little bit, and the thermostatic expansion valve could try to compensate in some of that. one of the things we have to be very aware of when we're using electronic expansion valves is that when we're reducing that airflow, it's really going to start reducing capacity of the system, because that EXV is going to be so finely tuning that refrigerant flow along the way. We still have that same function in thermostatic expansion, but once we get into electronic expansion, it's real critical to understand the airflow operation. And then when we move into inverters, it's a whole other story with our airflow.
Yep, absolutely. Sensing bulb location versus a TXV temperature, sorry, not a TXV temperature probe, a temperature probe to a EXV controller. They perform very similar functions, and in general, they should be mounted in the same location. So when troubleshooting, we kind of referenced this earlier, it's important to check it out. For a TXV bulb, it's important that it's strapped down. There's a good strong bulb strap giving it a good connection. Copper is better than a hose clamp, but a hose clamp can still do a pretty good job. Both of those are way superior to a zip tie. Zip ties, especially for a TXV bulb, don't do a great job. When it comes to a temperature probe, a lot of the same things. You prefer to have something stronger and more rigid than a zip tie. It's better if it's insulated. That helps it to get a better sense of the temperature. And when it comes to troubleshooting, especially with a system that's been around for a while, I always I always warn people to look for Armaflex that's been peeled away and you get that black gunk. If you have a TXV bulb or a EXV temperature probe that's on top of that gunk that's still left behind when you peel away Armaflex, that TXV or EXV is toast. It's not going to perform well because you're not actually going to be measuring the temperature of the suction line. It's going to be overfeeding a ton until you've so much liquid flooding back that then finally the cold temperature starts to make its way through that gunk of Armaflex, and then it slams itself shut again. So yeah, that's definitely a thing to look for. So yeah, that's an important consideration.
What about insulation differences? Do we see much difference between the amount of insulation required for a thermostatic expansion valve and the temperature thermistor for an electronic expansion valve?
I've not seen any big difference in the requirement there. You can get away with not using it and it'll still work, but it's better to have it. And I don't really think I've seen a big difference between the two in terms of whether you need or don't need insulation and whatnot. I do think some of it does depend on if you're in the airstream or not. If your suction line is outside of the airstream, then not having insulation becomes less of a problem. But it's always better to do it because then you're getting a true measure of the suction line, and then you're going to be more accurate to measuring superheat.
Jason had another question that is a really good one, because I've encountered this before, and I'm not sure, and it might not even be something that can be answered. From a manufacturer perspective, is it acceptable to use a heat transfer paste in between a thermistor bulb and the tubing itself?
Thermistor bulb and the tubing itself. So it's not something I have a lot of experience with testing. I will say that on a temperature well for
Yes.
a temperature sensor, generally you're recommended to have the thermal paste in there because you're putting like metal up against metal, and like you kind of need that paste to help make sure that it does good heat transfer. So in a well sensor scenario, yes. When we're talking about putting it on the surface, it's just not something that I've had a lot of experience testing. So that's one where I don't have a strong answer for you either way.
No, and that's perfectly acceptable because I've never encountered it in an installation manual. I have seen technicians do that, though, as a way of keeping moisture from having that potential getting in between the thermistor bulb and the copper. But I've not seen any type of technical bulletins on that. So, completely understandable. It's not in the scope of conversation. But the well, it's a perfect example of why there should be.
I myself noticed a question over there on the side that I can answer. It was someone saying, is 410A used for low temperature? And they're asking because in the slide I had up, there was a 20-degree evaporator temperature. And actually, sometimes 410A is used in ice machines. There are some lines of ice machines, like kind of like the one you'd find in a hotel. I don't know why there's so many ice machines in hotels, but anyway, that's the example I like to go with. There is certain manufacturers that use 410A for that, and I don't have a good answer as to why. I was not involved in the designs, but you can find it in ice machine applications. So I assume that's whoever was making that slide made it for an ice machine situation. So.
Yeah, and I actually encountered a few very interesting walk-in coolers that were used in McDonald's for a period of time, where they used residential air conditioners that had plate heat exchangers. And so they were actually using refrigeration evaporators and residential air conditioners for their walk-in coolers. And they did run a very low evaporator temperature.
Interesting. Yeah.
Oh, yeah, they were oddballs. The first one I encountered, I thought that somebody had made a mistake, but they had a residential condenser that was designed for higher capacity, lower temperature operation, and used refrigeration evaporator. And yeah, it was an interesting system. So there are a few instances where R410A is used for lower than the medium temp operation that we encountered traditionally.
Interesting. Yeah, it happens. Yeah, and if you think about it, like 410A is used in a heat pump, and even before you get to like a cold climate heat pump, they're still used in sub-zero temperature, below 32 degree, below freezing temperatures pretty often. So it makes sense that it could be used in a refrigeration application. So yeah. Valve blockage. It's kind of a simple thing, but contaminants inside a system can plug up a TXV and it can plug up an EXV, and it's going to have a pretty similar effect on both. So I've got here some examples of pictures of just different valves Danfoss has taken apart that have contaminants. I think all of these are TXV examples, but it looks the same inside an EXV, whether it's a scale from not flowing nitrogen, whether it's burnt oil, whether it's some sort of other sludge that comes from chemical reactions from having random outside contaminants. It can definitely gunk up and restrict flow through an EXV.
One thing that's worth mentioning at this point too, because I've had a lot of questions on this in the field. Many times in a thermostatic expansion valve, we have a removable screen in front of the valve. Do we see the same type of screens being used in electronic expansion valves?
Yeah, I haven't seen that sort of design in a lot of supermarket systems. I know what you're talking about, where they've got a TXV that's got this right angle to it, and there's a little screen that you can unscrew from it. I don't see the same thing in either air conditioning TXVs or in EXVs for any application. I don't want to say it couldn't be done, and I shouldn't say that it doesn't exist. I'm saying I haven't seen it, and I don't think Danfoss offers one.
Yeah, that's one of the things that I wanted to make sure people are aware of, because if you're used to seeing a screen in front of that metering device, it may not or likely will not be there. I have seen some system designs that have a screen but not a filter dryer. When we start looking at these critically charged and high efficiency systems, the less restriction in the system possible, the better it's going to operate. But on the technical, on the service side, it's important to know that improper installations and repairs can absolutely affect an electronic expansion valve more than it could on that thermostatic expansion valve.
Yep, absolutely. So when troubleshooting a EXV, I like to try and isolate which component in this whole network of things have to all work together is not potentially working right. With a TXV, you've got the bulb and the equalizer. It's kind of all part of one thing. It's one item, even though it's got different parts of it that kind of branch off and do its own things. But with an EXV, it's really important to figure out, okay, do I have a valve problem? Is my controller not working? Is my transducer not reading anymore? A temperature probe. And, a lot of the advice for how to troubleshoot through this, you kind of need to know what controller is being used by the manufacturer. And you have to kind of troubleshoot that based on the manufacturer's recommendations, based on what it's able to communicate out. But I've got some good general advice for things that you can do when you encounter one to try and troubleshoot your way through it. And it's kind of all, to me, it's always based around how do I start narrowing things down? How do I start chopping? Okay, I know this is working, so now I can turn my focus to this. And it's how do I kind of rule certain things out? Kind of process of elimination troubleshooting is generally how I think through things.
Yeah,
so
I agree.
So I just happened to notice here. Can I talk about bipolar and unipolar stepper motors? That could be a whole topic in and of itself. The difference between bipolar and unipolar stepper motors. I can get into it a little bit here because I've got some pictures to help show it. The unipolar stepper motors, they tend to be these smaller EXVs. They're very popular in VRF and residential HVAC systems. Generally small capacity, single-digit tonnages. One of the main ways you can identify them is that they will have 5 or 6 wires on them, because there'll be 4 wires that get power and then either 1 or 2 wires that are a neutral. And that's a unipolar valve, different type of design. And then there's the bipolar valves that are typically larger EXVs, and there will just be 4 wires there. And they're different technologies. The unipolar is a little bit lower priced, and it's a little bit simpler in its design. The bipolar is a little more expensive, but when you've got a bigger valve, it's a more efficient way to operate a stepper motor. So they both got their advantages and disadvantages. I've got a presentation somewhere else on my computer where I try and explain the differences in more details, and it takes 20 to 30 minutes to go through. So yeah, the bipolar motors do have more torque, and that's why they're better on larger systems when there's more refrigerant it has to push against. So for the purposes of this slide, since I'm getting into troubleshooting, the goal is to try and eliminate, hey, does my stepper motor work? And one of the ways you can check, does my stepper motor work, or has it been damaged? Does it have an electrical burn to it? Is to ohm it out. And when it comes to the bipolar stepper motors, you compare everything to your neutral wire, and then you check, what does it ohm out properly. Here's an example of one of our EXVs, an ETS6, and that one's supposed to ohm out at 50 ohms. You'd have to check with each individual manufacturer, what it should be. But generally, it's a double-digit number. I've seen different values for different manufacturers. Generally, it's a double-digit number. And if you find that this is way out of whack, or it's open, or it's closed, you got continuity, that would give you a real indication that you've got a problem. And the same thing happens with the bipolar stepper motors. But there you are measuring the resistance between the A's and the B's. You're measuring it across certain points. So
that's a really good slide, because I've been looking for what tolerance is acceptable on our resistance reading for our windings, and I see that you have a plus or minus 5. So we're looking for a plus or minus 10% as an acceptable range then within our resistance readings.
Yep, that's the number that I see for most Danfoss EXVs. I don't want to make promises for other manufacturers, but 10% is usually a pretty good rule of thumb.
Yeah, no, that's great. I've been looking for that because a lot of our equipment manufacturers don't specify the tolerance. And so most of my classes, I offer that I believe that 10% is an acceptable range, but I didn't have any validation from equipment manufacturers. So to see a valve manufacturer saying that it is a good range to be within, I'm grateful to see that. I feel better about what I've been telling people.
Good. So that's a way you can just troubleshoot, give yourself a quick, easy check. Hey, does my motor work? Just pull the wire off the controller and measure it that way. Also, too, when the cable is separable from the EXV, you can just simply check, do I have continuity back to my controller? Did a wire get cut somewhere between where the evaporator is and the controller? If you're in a packaged unit, it's not very long. unless the opening of one of the cabinet doors, literally cuts the wire, which would be pretty silly if that's how they laid out the wiring, but that things happen. That's probably not what it is. But if you've got a split system and you've got a long run of wire going in between two units that's 50 feet long, that's something to check. Is it just a simple breakage in wire?
Brian, before you get to that next one, I have a scenario that I'm hoping there might be some more information on. It's something I've witnessed in the field before.
Okay.
If I would say, like with this, say we had four winding connections or 5 winding connections, and we found one of those pair to have an open resistance, what would we potentially see in the operating of the valve?
So if you see open resistance, there's not continuity. I mean, what that's probably indicating to me is that one of the poles in the step motor is burned out, so it's probably not going to drive open or closed, and it's probably going to just be stuck wherever it is. And as a result, if it's stuck at 20% open, like it's going to feed some. You won't shut off on low suction pressure, but you're certainly not going to do much cooling. Although depending on what the situation is, maybe 20% it'll allow you to limp along pretty well. It just kind of depends. Wherever it was when it died, that's where it's going to be.
And that was one of the scenarios that I encountered on a new piece of equipment. It's been quite a few years ago, but it was a newly installed system that was only getting partial capacity. And what we found was that it was calling for full capacity, but we had one of those windings that was open, and so we could only get a partial capacity out of the system. And you're right, it would shut down completely. And so my opinion was that we could, depending on what phase it is, we could get some partial opening or closing, but not 100% control of that electronic expansion valve. And we may not get an error code unless the controller was designed to read resistance through the connections, but it's not a common practice that I've seen.
Yeah. And I think that does help segment me into another idea that these EXVs, they're dumb valves. They only do what they're told. All the brains is in the controller. The controller has the brains. And another thing about them is like the EXV doesn't communicate back to the controller. The controller tells the EXV to move, and the controller just has to assume the EXV did what it was told. If one of the poles inside of the motor is burned out, well, then it's not going to do what it's told. And you might have a controller that thinks the valve is 100% open because it's told it to go 100% open, but it's lost steps, when one of the poles is burned out, so it's not actually able to do all the number of turns that it's supposed to do. And the controller thinks it's 100% open, but in reality, the valve is 30% open or whatever the number is. And that might be how you get your alarm. You get the alarm, that you get a high superheat alarm because the valve is 100% open and it can't do anything to bring the superheat down. And it's been high superheat for 2 hours. And now the chiller is kicking out a alarm for high superheat. Just sort of depends. So that's a way you can find things. But the EXV is a dumb valve. It only does what it's told, and it relies on the controller to know where it's at. And that's one of the reasons why when at initialization, an EXV is always driven 100% closed, because when a controller doesn't have power to it, it doesn't know where the EXV is. So whenever a controller gets itself first powered on, there might be a few seconds where it's kind of waking up. But once it's awake, the first thing it does is it drives an EXV 100% closed, whatever the total number of steps for that valve is, it drives it fully closed, and then sometimes a little bit extra just to make sure they get it fully closed. And then it starts controlling to get it to open to where it needs to be. And but this gives you a good advantage if you understand those controllers, to troubleshoot that controller. Is there a problem with the controller? If you pull power to your EXV controller, it's probably good to do this when the system's already shut down, so that way you're not gonna cut out the suction pressure to it. But you have the system off, but the controller is still kind of operating independently. It's doing its own thing. You can pull power to your controller, plug it back in, and then you can put your multimeter, you set it to volts AC, and you put it on 2 of the terminals where power is going to be going to it, and then you look if you're getting voltage. And if you're getting voltage, generally between 12 and 24 volts, that's giving you an indication, all right, my controller is at least providing power to the EXV. So it gives you an indication that like the driver and the board itself isn't burned out. You didn't get a burn inside the control board. There wasn't a a lightning strike and you got a power surge to the controller that burned out the controller. And where knowing more about the controller itself can help, because there's all kinds of different flashing lights that tell you if you've got problems. Here's a Danfoss controller that we make that doesn't have like built into it a display. It can communicate out via Modbus, so it might be on the system controller's display. But on our thing, there's not a display itself. But we do have little flashing lights, and we flash lights indicating when the valve's closing. When the valve is fully closed, it stays steady red when it's fully closed. We flash green while it's opening. We say steady green when it's fully open. And we flash both lights at the same time just to indicate there's an alarm. And it means the controller knows something's not right with it. And we have the ability to communicate that out via Modbus to the system controller. But it depends on that manufacturer as to whether or not they're reading that and how they're able to communicate that out to you. Because there's all different levels of tech. There's chillers now that will send you an email when something goes wrong, and there's other ones that are they don't have any connection to the outside world. They're their own independent thing, and it's kind of the way it is. But a lot of these controllers do have lights on them to flash and give you some sort of indication what's happening. And that's a good place to look, and helps you figure out, well, what's working, what's not working. If you never see any lights light up on one of these boards, it gives you a good indication the board doesn't work. There's either there's no power going to it, or it's burned and died, and the power's not doing anything to it.
Yeah, completely makes sense.
And another thing you can do too is, if it's all wired up when that control board starts up, is you can usually hear or feel an EXV. So this that tapping sound you were hearing there, that's the EXV making a sound and banging against this little table. And oftentimes it's not that loud. So if there's a compressor running, you're in a machine room or something like that, it might be hard to hear. But if you hold on to that valve, you oftentimes can feel it. And then if you've done it enough times, you can actually hear and feel the difference between an EXV when it's like moving around versus when it's hit its seat and then it's like knocking. And that sound you were hearing here, that's actually a EXV that's hit its seat, and it's like it can't go any further. It's already all the way closed. So, and you can see here too, I've got the voltmeter up on it, and it's measuring 12 volts. And these controllers do send out pulses of 12 volt DC power, but because it's doing it so many times a second, you have to set your meter to AC to actually be able to see it. So,
but it is a DC voltage that is being supplied to the control, or
yep.
From the control.
Yeah, the controller is providing DC power, but it's doing it really quickly. It's kind of like that. If you're familiar at all with operating with a VFD, right, brings in AC power, and then it sends pulses of DC power out to whatever motor it's controlling, but it does it so fast, like, it might be sending out at 60 hertz, 60 times a second. And that way, to pick it up, you need your multimeter to be set to AC. Otherwise, either it'll just say 0 or it'll be confused, or it depends.
Now, on our thermistor, temperature thermistor, and our pressure transducer, will we still see a 12 volt DC signal, or will it be something different?
So most of the transducers are not going to be 12 volts. The most common ones that Danfoss sells are at 5 volts, but there are different ones out there. And the way that the most common one that Danfoss sells works is you send a 5 volt signal from the controller to the sensor, and then the sensor sends back a 0 to 5 volt signal based on what the pressure is. 5 volts being the highest pressure, 0 being the lowest. And so you can potentially, depending on how it's set up, read the pins coming back to see, hey, am I getting any signal coming back from my transducer? And you can put your gauge on it and compare, what you're seeing, and that might be a way to give you an idea.
So if we have a concern that potentially our pressure transducer is not sending the correct signal back to our controller, we can use our voltage chart and compare pressure to the output voltage of the transducer, and that should get us back into range and see if we're there or not. Very good.
Yeah, and temperature sensors, they operate entirely on resistance, so you can like ohm them out and see what you're getting. You might be able to use that to help you indicate. Probably the main thing you're going to see there is if you either get resistance or you don't. If you don't, it lets you know the wire's cut or something. And that's probably as far as you'll get with that. But even there, you could track down. Okay, this is a 2K sensor, meaning it's meant to be at 2,000 ohms at the room temperature, I believe. Don't quote me on that part, but you can track down a chart if you really want to troubleshoot your temperature sensor. Like, hey, is it reading the right ohms for what the temperature is?
And it's important to know that not all thermistors operate in the same resistance. It's important to look at the instruction manuals to determine what thermistor range that you have. You could have a 2K, 5K, 10K, 50K, depending on its application. Do you have a common resistance? And yes, Jason, I typically see that too. Most of our thermistors have a resistance around 76, 77 degrees as their baseline. And so like with Danfoss, is there a common resistance that we might see, or common thermistor range?
10K is the most common one that I see, but I would not stick to that being like, the most common. Just that's the one that I'm used to seeing, but it's not like the 5-volt pressure transducer where I'm pretty confident that's the most common out there when it comes to temperature sensors. 10K is probably just the last one that I saw. I'm not super confident which one's the
Sure,
most common there.
Yeah, that's why I just wanted everyone to know that there are a variety out there. So whatever piece of equipment you're working on, make sure to verify what the resistance is and use the chart from that manufacturer.
Yep, absolutely. And this is the end of my slides. This is the last one that I had. So we're getting near the bottom of the hour. So I'm open to answering whatever other questions people might have.
No, I mean, that's perfect. Yeah, we're right up there. We still got a few minutes left. Anyone has any questions about understanding the differences between thermostatic expansion valves and electronic expansion valves, how they operate? We really, when we look at operation of either, we're using an input to manage an output. With our thermostatic expansion valve, we're using our thermistor bulb and the pressure being applied on our device to manage the output, the flow of refrigerant through the valve. And with our electronic expansion valve, we're using our typically two inputs. We're using a temperature thermistor and a pressure transducer to calculate where our output, our driver, should be managing the same flow of refrigerant. We're just doing it much more accurately. And a lot of people get hung up on that fact of understanding that they're really doing the same thing. We're just doing a much more accurate version of that in that electronic expansion valve. And it's critical when we start looking at efficiency. The more efficient of a piece of equipment that you're going to work on, the more likely you're going to encounter electronic expansion valves. When it comes down to a metering device, if we think about, well, what is the ideal range for superheat or subcooling? Theoretically, to get the maximum efficiency out of our evaporator, we want the minimal superheat possible above zero. And on our condenser, we want the minimal subcooling below zero so that we're using the maximum efficiency of our coils. But the manufacturer could specify a range in that, and the closer we can maintain to that range that is designed at, the more efficient, the more effective that system is going to operate altogether. And so I'm a big proponent of electronic expansion valves. Once you get comfortable with them, they really do a nice job. They're so easy to diagnose. I mean, the only failures that I have ever seen mechanical has been because of poor installation practices where people are not flowing nitrogen on installation, and then we start getting our debris that is going to do contamination and damage to our internal metering device. They very rarely fail mechanically on their own. And so typically it's now in our stepper motor. And most of those are a quick, easy removal and replacement if we do find a defect in one.
Mm-hmm.
Yeah, and you're right, Jason. I mean, some of those lower design temperatures, like in some centrifugal chillers, we may see that superheat running as low as 0.5 degrees. That's because we're trying to get that maximum efficiency without any potential of getting liquid back to our compressor. We don't want any liquid back in that pump. Oh, yeah, that is a great one. And that is actually probably a whole conversation that we can have. It goes back to the same conversation of operation. I have only found a very few, probably less than a handful, of thermostatic expansion valves truly bad in the industry. They could have been damaged from improper installation, but typically they're a very reliable operating instrument. Now, the variables that can cause it to adjust, on the other hand, uh, could be the things that could be affecting it. So we always start with standard practices. Is airflow correct? Then we can move on to, is refrigerant charge correct, and how is our superheat and subcooling working? But the airflow across those coils are always the most important thing to check on any thermostatic expansion valve.
Yeah, yeah. I mean, what indicators? Superheat being off is the first one, but you then have to go verify. Well, if the superheat's off, but the subcooling's uh, near zero as well. Well, fix the subcooling and then see if that fixes the superheat. It kind of has to be process of elimination, and when it comes to like contaminants blocking up a TXV. When we get TXVs back, there's two major things we run into: no fault found, and then filled with contaminants. Just about everyone we ever get back is that way. Sometimes we can see that it's burnt up, when it's being removed. Sometimes it's like we can't evaluate it to figure out if there was something wrong with it. But we get a lot of EXVs sent back to us, and it's almost always filled with contaminants or no fault found. And when it's no fault found, we assume that means it was diagnosed improperly, or there was another problem inside the system that prevented it from working right. And oftentimes replacing a TXV ends up working because in the process, you're pulling out the charge, you're replacing the filter dryer, you're recharging it, you're charging it correctly. While you're doing that, you're maybe checking the airflow again, you're cleaning the condenser in the process. Usually in the process of removing a TXV and reinstalling it, you're kind of resetting the whole system, and you'll fix whatever other problems in there in the process without realizing that's what you did. And look, if a TXV is plugged with contaminants, there is no other way to fix it than replacing it. So, I mean, that is the right call in that case. But yeah.
If there's ever any shareable data on the percentage of no fault found warranty thermostatic expansion valves, I would be very intrigued with that, because I've talked to some of our compressor manufacturers that will validate that it is an exceptionally high number, showing that many of our components in the industry are unnecessarily replaced simply because we didn't understand how to properly diagnose those to begin with. All right, everyone. I sure appreciate you hanging in. It's been a long day. We've been putting in 13, 14-hour days here at Skills USA. I'll encourage you to come back and check some of the videos that we'll be sharing. I just put one on LinkedIn last night, and I came back, did some editing on. And we'd like for you to reach out to Danfoss to learn more about education and resources from Danfoss. Can you tell us, Brian, about training or educational resources that are available through Danfoss?
Yeah, through our website, we have access, or we give access to a lot of training on the various components that Danfoss makes, which primarily fall into the categories of valves, compressors, heat exchangers, both brazed plate and microchannel, as well as sensors, whether it's pressure transducers or A2L refrigerant leak detector sensors, which is a new product for the industry, a new product for us, and that I'm just mentioning now for the first time as we're trying to sign off. So I won't say any more before I open up a different can of worms.
No, that's quite all right. Well, Brian, Danfoss, thank you so much for hopping in here to give us some more education from firsthand information. That's really the way that we should all be learning, directly from the sources of content. And I'm sure there are plenty of things that we can dive into deeper for those of you that are still hanging in with us. I encourage you to let us know in the chat or send me an email of other topics that we can dive into with Danfoss. We started talking about the different types of controls in our expansion valves, or electronic expansion valves. Maybe that's something we can do down the road, but I encourage you to let us know what you need, and we'll make sure that we get the education and resources for you. All right. Well, thank you, sir. I appreciate you hanging out with us for tonight. And we'll see you all next week on Did You Know, the ESCO HVAC show. Bye, everybody.